Today we begin Chapter 5, and we're going to do two sections in Chapter 5. And Chapter 5 is all about polygons. So we talked about triangles in the last unit, and now we're going to extend that to other polygons beyond triangles, so quadrilaterals, pentagons, hexagons, and so on and so forth. But today we're going to talk a lot about angle measurements within polygons and come up with basically our first formula of the year that we're going to use to calculate the total angle sum for any polygon as well. So on number one, we're starting off with find the sum of all the interior angles of each quadrilateral. So in a rectangle here, we have ABCD rectangle, and of course all the angles in a rectangle are 90 degrees. So if we add those up, we have a total of 360 degrees. So in a triangle, the angles sum up to 180 degrees. In this rectangle, it sums up to 360 degrees. Let's see if that's true for other quadrilaterals beyond just rectangles. Remember, quad means four, so when we say quadrilateral, we're talking about any polygon with four sides. So in the second example, EFGH, we've got 43 degrees plus 95 degrees, plus 114 degrees, plus 108 degrees. If you add up those angles, we also get 360 degrees. And here is what you might recall as a concave quadrilateral in our last example here, JKLM. Concave meaning one of the sides is pushed in, kind of caved in, so we actually have an outside diagonal here. Now, in a concave quadrilateral, it's a little bit tricky to talk about interior angles because this technically isn't really an angle. It would be called a reflex angle, but the angles that we had talked about previously had to be between 0 and 180 degrees. But even a reflex angle, if we think about the angle here and subtracting it from 360 degrees, we get the amount of rotation around here to be 238 degrees. So even in that situation, if we take 70 degrees plus 38 degrees plus 14 degrees plus 238 degrees, we get an angle sum, once again, of 360 degrees. So even when we include reflex angles, we do get the total angle sum to be 360 degrees. So summarizing this, all quadrilaterals have a total angle sum of 360 degrees. Usually we're referring to convex quadrilaterals, but in concave quadrilaterals, we basically have that same idea hold true. All right, so we knew that triangles added up to 180 degrees. We now have talked about quadrilaterals that sum up to 360 degrees. If we went through and measured the angles in a pentagon, five-sided shape, five-sided polygon, we would find that the total angle sum is 540 degrees. In a hexagon, a six-sided polygon, we get a total angle sum of 720 degrees. Hopefully you are starting to see a pattern here. Our next one is a heptagon. Heptagons add up to 900 degrees. Octagon adds up to 1080 degrees. Nonagon, you'll be responsible for knowing all of your polygons up through at least 12. Usually we stop at 12 in terms of what we are referring to, at least by memory. So that would be 1260 degrees, 1260. 10-sided, decagon. Decagon. Total angle sum, 1,440 degrees. Undecagon, 11 sides. Total angle sum, 1,620 degrees. Dodecagon, 12 sides. We get a total angle sum of 1,800 degrees. All right, so there is our angle sum table from sides, from a triangle up to a dodecagon, 3 sides, up to 12 sides. Now, since there is a pattern here, we should be able to come up with our first formula to relate the total number of sides to the total angle sum. So why don't you take a minute and see if you can figure out what that formula might be. You probably saw a pattern already. Many of you guys probably noticed that as we increased the side, we were adding 180 degrees. So we added 180 degrees here, added another 180 degrees, added another 180 degrees. So every time we add a side, we're adding 180 degrees to the total angle sum. All right, well, what sort of relationship is this? When you are adding the same amount each time, or for that matter, subtracting the same amount each time, but in this case we are adding 180 degrees. What's that you say? That's right. It is linear. As a linear relationship, whenever you add or subtract the same amount each time, the x values, so you can kind of think of this as the x values and these kind of as the y values here. Every time we go up one x value, we add 180 degrees. It's linear, which means 180 is the what? It's the slope, okay? So 180 degrees is the slope of our linear equation. So our formula right down here is going to be a linear equation, or it's going to be a linear relationship. 180 is our slope. Now, what's the other thing we need in a linear relationship? At least with our intercept form, slope-intercept form, we need a slope and we need a y-intercept. Well, what would the y-intercept be here? What would be our starting amount? Well, in our table, we're kind of starting at 180, but that's not really the y-intercept, right? Because that has an x value of 3 to a y value of 180 degrees. What if we trace our pattern backwards? So we see that, what if we had theoretically 2 sides, 1 side, 0 sides? That would not be a polygon, but we could still think about the pattern itself going backwards here. And instead of adding 180 degrees, if we went backwards, we would be subtracting 180 degrees. So if we went backwards 1 step from here, our angle sum, theoretically, at least with the pattern, would be 0 degrees. All right, going back 1 step here. 0 minus 180 gets us to negative 180. So kind of going backwards here. And then 1 more step, we go back another 180, we get negative 360. So if we traced our pattern backwards here and think of this kind of as the x values in our table and the y values in our table, the negative 360 is across from an x value of 0. Therefore, negative 360 is like our y-intercept value. If we were graphing all of these as points on a graph, like a scatter plot, we would see, if we went backwards, we would see that the line would eventually cross the y-axis at negative 360. So let's think of this as an equation then. If 180 is our slope, you can almost think of this as a y equals mx plus b equation. If 180 is our slope, we've got 180. Instead of using x, we're going to use n to represent the number of sides. Right here, so the number of sides is n. So 180n minus 360. Or if you prefer, negative 360 plus 180n. So that is our formula, at least our first version of this formula. We can use this to calculate the angle sum for any polygon. So if I wanted to know for a 10-sided polygon or a 20-sided polygon, let's say 20, I would take 180 times 20 minus 360, and that would give me the total angle sum for a 20-sided polygon. If I wanted to know for a 1,000-sided polygon, I take 180 times 1,000 minus 360, and that would be the total angle sum for a 1,000-sided polygon.